This is part 3 of a series on decision trees. Continuing from the last video, let's look at ID3 decision trees for classification. This video was produced in Korean and then translated into English. The voice was generated using text-to-speech. In the last video, we looked at how to use information gain to create an optimal ID3 decision tree. In this video, we'll look at information gain ratio and how to use it to generate ID3 decision trees. We will also look at tree pruning based on confidence intervals. Finally, let's implement a simple ID3 classification model. Now let's take a look at the information gain ratio, IGR. In the last video, we used information gain to build an ID3 decision tree for this dataset as follows. The feature age yielded the greatest information gain, followed by P-class and then sex. So we first split the age feature, then split the P-class, and finally split the sex to create a tree like this. But there is one problem here. The more categories a feature has, the larger its IG tends to be. In this dataset, P-class has 3 categories. Sex has 2 and age has 4 categories. Since age has many categories, the information gain will also be large. To solve this problem, we apply some kind of penalty to features that have many categories. This is the idea of IGR, the information gain ratio. In conclusion, when IGR is applied, P-class is split first. Before looking at IGR, let's first look at SI, which is split information. SI is a kind of penalty. The formula for calculating SI is as follows. Here, N is the number of categories, and the capital letter N is the number of data points. Let's use this formula to calculate the SI of P-class. The root node has 18 data points. Among them, there are 6 data points with P-class of 1, 5 data points with P-class of 2, and 7 data points with P-class of 3. The SI of P-class comes out to be 1.57. Next, let's calculate the SI of sex. There are 11 data points where sex is male and 7 data points where sex is female. Then the SI of sex is 0.96. If we calculate the SI of age in the same way, we get 1.99. Age has many categories, so the SI is high. Now let's use these SI values to calculate the IGR for each feature. IGR is defined as the information gain divided by the SI. The IG of P-class is 0.08, and the SI is 1.57. Therefore, the IGR of P-class is 0.051. Calculating the IGR for sex and age in the same way yields 0.031 and 0.046, respectively. You can see that the P class has the largest IGR value. The feature age has a large information gain. But since it has many categories, its SI is also large. Therefore, the IGR becomes small like this. Applying IGR first splits the P-class feature, then the age feature, and finally the sex feature. Next, let's look at tree pruning based on confidence intervals to prevent overfitting. As the depth of the tree increases, overfitting may occur, so pruning the tree is necessary. Let's look at the example below. In this example, node B is split into 3 child nodes as follows. Let's use pruning to determine whether it's better to split this node like this or not. First, let's calculate the misclassification rate before splitting node B. Node B has 14 data points like this: 9 blues and 5 reds. Since blue is the majority and red is the minority, the 5 red data points are considered misclassified. Therefore, the misclassification rate can be calculated as 5/14 or 0.357. This misclassification rate is a sample proportion, as it is the result of a real data sample. Next, let's calculate the confidence interval for the population proportion. The formula to calculate this is as follows. F is the sample proportion, N is the sample size, and Z is the critical value from the standard normal distribution. Here we used a Z critical value of 1.64 for the 90% confidence interval. By substituting the sample proportion F, the critical value Z, and the number of data points N into this formula, the population proportion is calculated as follows. The results range from 0.147 to 0.567. We can be 90% certain that the true misclassification rate that led to the observed misclassification rate of 0.357 will be between 0.147 and 0.567. The upper bound is 0.567. Next, let's split this node into 3 child nodes and calculate the sample proportion and population proportion. For each child node, the sample proportion and population proportion are calculated. The first node has a total of 6 data points, 2 of which are minority data points. Therefore, the misclassification rate of the first node is 2/6, and that of the second node is 1/2, and that of the third node is also 2/6. These are the sample proportions F. Next, let's calculate the upper bound of the population proportion. If we plug the F value of the first node and the N value of 6 into this formula, and calculate the upper bound of P, we get 0.649. Calculating the upper bounds on population proportion of the remaining nodes in this way gives the following results. If we calculate the weighted average of these 3 results, we get 0.711. And if we calculate the weighted average for the sample proportions, we get 0.357. This is the average of the lower and upper bounds of the population proportion P. The average of the lower and upper bounds of the population proportion P before splitting is 0.357, and the upper bound is 0.567. The average of the population proportion P after splitting is also 0.357, and the upper bound is 0.711. Since we are dealing with misclassification rate, the smaller this upper bound, the better the performance. There is no need to consider the lower bound. Therefore, the case where this value is smaller, your 0.567, has better performance. This means that the performance before splitting is better. Therefore, it is better not to split node B into child nodes. Pruning made the tree on the left simpler, like the one on the right. Next, let's look at another example. In this example, node B is split as follows. The sample and population proportions before splitting node B are the same as the results on the previous slide. In this case, let's also calculate the sample and population proportions of each child node. The first node has a total of 5 data points, one of which is minority data point. Therefore, the misclassification rate of the first node is 1/5. That of the second node is 0, and that of the third node is 1/6. The misclassification rates of the child nodes are lower than the results in the previous slide. Calculating the upper bounds on the population proportion of these nodes in the same way as before gives the following results. And calculating the weighted average of these values gives us 0.354. If we calculate the weighted average of the sample proportions of each child node, we get 0.143. This is the average of the lower and upper bounds of the population proportion P. Let's compare the upper bounds of the population proportions before and after splitting node B. After node splitting, the upper bound of the population proportion is smaller. Therefore, it is better to split the node B. Next, let's write code that performs classification using ID3 decision tree. We use the decision tree ID3 package to implement the ID3 model. Import the ID3 estimator class like this. Let's classify the Titanic dataset. We will only use 3 features: P-class, sex, and age. Load the Titanic CSV file. This dataset consists of the 3 features above and the target labels survived. The input of this model is 3 features, and the desired output is the target label. Convert the feature sex to have 0 for female and 1 for male. And we use Panda's QCut function to transform the continuous feature age into a categorical feature with 4 categories. We then split this dataset into a training dataset and a test dataset. Now we create an ID3 decision tree model. Let's apply IGR and also apply pruning. Fit this model to the training dataset. Next, we predict the target label of the test data and measure the accuracy. And we also predict the target label of the training data and measure the accuracy. Finally, we visualize the trained tree. The dataset contains a total of 714 data points. The accuracy on the test data is 78.32%. And the accuracy on the training data is 79.33%. The tree that has completed training looks like this. In the previous example, P class had the highest IGR. That was the result of using only 18 data points. Using all 714 data points, the IGR for sex is the highest like this. In this tree, sex is split first, then P class is split, and finally age is split. And you can see that the pruning has occurred at this node and this node. Pruning prevents these nodes from splitting further. Let's run this code. The result came out like this. And the tree was displayed like this. The accuracy on the test data is 75.98%. And the accuracy on the training data is 80.56%. So far, we've looked at the information gain ratio and also looked at pruning. And we also implemented an ID3 classification model. In the next video, we will look at the regression using ID3 decision tree.